Alright, here we go. We're finally halfway through the year, past that halfway mark, and into the third marking period with the dreaded IA number 3. Just so you know, guys, this is notoriously the hardest IA that we've usually given over the past couple of years, because this is where the topics get very mathematical, and if you're not careful with the math, you will get screwed. Alright, so this IA covers gas laws and mole chem. We haven't gone exactly that far into the mole chem unit, so a lot of this will definitely repeat a lot of gas law questions that we've already gone over and studied in the past, and some of the things you see in mole chem probably repeat from that quiz you guys took earlier. But anyway, let's start. So with number 1, if 6.02 times 10 to the 23rd molecules of N2 react according to this equation, N2 plus 3H2 yields 2NH3, the total number of molecules of NH3 produced is blah 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 blah. Okay, so we never really talked about reaction equations and how to read these coefficients, but what you can see is that there are coefficients here to sort of also indicate the moles there. So we could see that N2 has no coefficient, so we just assume there's 1. So there's going to be 1 N2 for every 2 NH3 in this reaction. Not necessarily that 1 N2 equals 2 NH3, that's kind of like an incorrect symbol, so let me get rid of that. So we could see that 1 N2 leads to 2 NH3. So there's like a 1 to 2 ratio here. So proportionally, we could think that if there's 6.02 times 10 to the 23rd molecules of N2, then there has to be double the amount. And so if we do the math, 2 times 6.02 times 10 to the 23rd will give us a value of choice 4. It's not proper scientific notation, but hey, it works for us. Number 2, which statement describes particles of an ideal gas based on the kinetic molecular theory? So we gotta think properties of an ideal gas. So some things about ideal gases is that they move very randomly. So there's random movement. No forces. Constant straight line. That's how they move. Constant straight line, random. No volume, basically. So looking at our choices, the best one that fits it is choice 3. Okay. Number 3. Which sample contains a total of 9.0 times 10 to the 23rd atoms? So here we have moles and particles. So we have to think about Avogadro's number. Okay. Let me do space for number 3 over here. So Avogadro's number is equal to 6.02 times 10 to the 23rd. And that's how many molecules or particles in 1 mole of a substance. So let's think proportionally. Here we have 9.0 times 10 to the 23rd atoms. We want to figure out how many are in 1 mole. So because I'm going to use the dimensional analysis method, if you want to cancel out the unit of atoms, it's almost equivalent to molecules. So you're going to get 6.02 times 10 to the 23rd on the bottom with 1 mole on top so we can figure out moles on the top. We're essentially doing 9.02 times 10 to the 23rd atoms. Oh my god, my pen's acting up. And we get 1.5 moles. Okay. So we can cross off choice 1 and 2 because both choices don't relate to 1.5. And now we're down to choice 3 and 4. What's the difference between 3 and 4? Now if you look at the formula, 1.5 moles of Cu has 1 atom for every 1.5 mole. And then here there's 2 atoms. So there's actually 2 moles of atoms for every 1 mole of H2. So in actuality, choice 4 would actually be double the amount of what we actually have. So it's choice 3. Number 4, sorry. A rigid cylinder with a movable piston contains a sample of helium gas. The temperature of a gas held constant as the piston is pulled outward. Which graph best represents the relationship between the volume of the gas and the pressure of the gas? So volume and pressure. We're looking at the relationship between volume and pressure. This is Boyle's law. And in this case, they have an inverse indirect relationship. So as you increase pressure, volume goes down. And this is more of an exponential decay. That's choice 1. Alright, so number 5, at STP, 4 liters of O2 contains the same total number of molecules as blank. So our keyword is that we are at STP with 4 liters of a substance. We're looking for same total number of molecules. So this goes into Avogadro's law. Okay, so we need the same of everything. Needs the same pressure, same temperature, same number of molecules. In order for that to happen, we need same volume. And that's choice 4. Number 6. A sample of chlorine gas is at 300 Kelvin and 1 atmosphere. At which temperature and pressure would the sample behave more like an ideal gas? So we're going to think most versus least, because you'll bet you there might be a question about least instead of most. So for most, oh, this line's too big. You want most ideal is high temperature, low pressure. Whereas least is high pressure, low temperature. So we're looking for something that's more, so we want the highest temperature and the lowest pressure. And that's choice 4. Number 7. The formula mass of a compound is the, alright, this is from that mole chem quiz, guys. What's the definition of formula mass? Well, what we do, we have to look at the atoms in a formula and add up their atomic masses. That's choice 1. Number 8. 1 mole of liquid water and 1 mole of solid water have different blank. Okay. So mole stands for pretty much the same amount. So if they both have 1 mole of the same substance, then they have the same amount of particles, same mass. Okay. For number 8, Same moles leads to same mass. Okay. If it's both water, they're both H2O, so the formulas are the same. And if they're both H2O, they both have the same molar mass, GFM. Same gram formula mass, which is 18 grams per mole. So it has to be choice 2 properties, because clearly liquid and solid are different properties, water versus ice. Okay, number 9. At 25 degrees Celsius, a gas in a rigid cylinder with a movable piston has a volume of 145 mL and a pressure of 125 kPa. Then the gas is compressed to a volume of 80 mL. What is the new pressure of the gas if the temperature is held at 25 degrees Celsius? If the temperature is held constant right here, then we don't have to worry about that one. And that was a brief little interruption. That was the door opening by your boy, Mr. Coutinho, my future successor to these chem videos. So once I'm done with chemistry, feel free to watch his videos for chemistry review. But you'll still see me for physics videos. Anyway, aside from that, okay, let's continue. Number 9. What is the new pressure of the gas if the temperature is held at 25 degrees Celsius? Let me get myself back on track. So then we are not worrying about temperature, so we're just doing Boyle's law. Oops. Okay. So taking a look at our combined gas law equation. Because temperature is held constant, we don't need to worry about these guys, get rid of them. And we're going to plug in things as usual. A gas has this original volume and this original pressure, so we're going to plug these in. 125 kPa times our volume of 145 ml equals our new pressure, P2, which we're solving for, and our new volume of 80 mLs. So look here, we're seeing that our volume is decreasing, so we should expect pressure to increase. So we're looking for a bigger number than 125. If you calculate it, plug and chug into your calculator. Hope you're chugging water. Okay, so 125 times 145 divided by 80, and you get about 227 kPa. Well, if you look at your choices, the closest one is choice 4. There you go, ladies and gentlemen. Number 10. Oh, I'm running out of room here. What is the total number of nitrogen atoms in 0.5 mole of NO2 gas? What is the total number of nitrogen atoms in 0.5 moles? So if we know that 1 mole, actually, let me bring this number 10 over here to this small area. Whoa, what the heck was that? Okay, let's try that again. One mole equals 6.02 October 23rd. Okay, we need to remember that number because it's not on the reference table. So 0.5 moles, let's think proportionally here. So we're going to cut this in half, and we should get 3.01 times 10 to the 23rd. And luckily, there's already 1 nitrogen atom in there. If we had multiple nitrogen atoms, that's when things get tricky, so lucky us. Should get choice 3. Now that saves me some room for number 11, which is a doozy whopper over here, because we're dealing with percent composition of sulfur. Okay. So we got 4 different choices, the 4 different compounds, and see which one has the greatest percent composition by mass of sulfur. Okay. So I've seen a variety of tricks. The proper way is to use the equation on the reference table. But here's a shortcut trick that I actually saw from a student while grading mole chem quizzes. Okay, not going to name the student. But here's the trick that I saw, which actually gives you the correct answer in all cases. Okay, so I already pulled out the reference table to the periodic table, because you're going to need this. Okay, so I already wrote here that sulfur is 32 grams. How did I know this? Well, you look over here for sulfur, and you see that it's 32 for its atomic mass. That's what you're going to use as your reference point for sulfur. Now you're going to look up the other four over here. Barium, Mg, Ca, and Sr, and luckily they're all in the same column over here, same group. So barium is 137. Okay, 137 grams. Magnesium is 24 grams. And calcium is 40 grams. And strontium is about 88 grams. What you're going to do to each of these numbers, if you want to find the greatest percent of sulfur, what you're going to do is you could take sulfur and divide it by each of these, or what you can do is compare each of them to sulfur. Okay? So, greatest percent. So you want sulfur to be the greatest, the higher number compared to the other elements. Okay? So, in this case, if you solve it actually, you'll get for barium is going to be, okay, for barium you get 32 divided by 137 plus 32. For magnesium you'll have 32 divided by 24 plus 32. Calcium will be 32 because we're talking about sulfur, and see how it compares to the others. 40 plus 32, and then strontium is 32 divided by 88 plus 32. Okay, so part over the total. So the total here combines both sulfur and the respective elements here, and so you should get these approximate percentages, and this is the proper way of doing it. If you look at each of these numbers, you'll see that barium is not our answer. I almost caught that. So it's actually magnesium. Magnesium is the one where sulfur has the highest, greatest percent composition. And if you look at the mass of magnesium, magnesium has the smallest mass. Compared to sulfur, sulfur will easily overpower magnesium, making sulfur the bigger element there. So if you want the greatest composition, then you want to see where it would overpower the rest of the elements. Whereas if you want the least, you want to see which element will overpower your target. So barium will definitely overpower 137 to 32. Sulfur will definitely overpower magnesium 32 to 24. And that was a whole long explanation. Choice 3. Okay, now we're going through 12 to 16. Number 12, which two gas samples have the same total number of molecules? So we want same temperature, same pressure, same volume. And those that have that same sort of stats, we can immediately cross off D for many of them because the pressure is different for D compared to the rest of them. So we're looking at A, B, and C, and we can see that B has a different temperature between A and C, so our answer is A and C. Looking across, they have the same stats. Choice 2. Number 13, what is the mass of 0.5 moles of CO2? Ooh, I love these questions. Okay, number 13 I'm going to do in this space right here. And my pen's acting up again. Okay, so CO2. We need to find the gram formula mass, or the molar mass, or the formula mass, as everybody calls it. So we got CO2. Oh, I'm just repeating things. I don't know what I'm doing. Okay. Gram formula mass. We have to look into each of these elements. There is one carbon with a mass of 12 grams. That you'll have to find on the periodic table. Plus oxygen. There are 2 of them. And the mass of oxygen is 16. So 12 plus 2 times 16, so 12 plus 32. This comes out to 44 grams per mole. Now, the next thing you're going to do is look at the reference table, table T. They have the equation for this, where it's number of moles equals given mass, which we're looking for, over gram formula mass. Oh God, my G looks terrible. Okay. They give us 0.5 moles. We're looking for given mass, and our gram formula mass is 44 grams per mole. So dimensional analysis, you can see units cancel out to give us grams, and we get that our answer is 22 grams and 0.5 moles, because this gram formula mass shows you the mass per mole. 22 is our answer. Okay, table H, which is needed for number 14. Which statement concerning propanone and water at 50 degrees Celsius is true? So let's find table H. Let's pause. Okay, so now we got table H present, and we're looking at the differences between propanone and water. So we have to compare its vapor pressure and intermolecular forces. First, let's look at 50 degrees Celsius to compare vapor pressure. Okay, so I'm going to circle where these points are. At 50 degrees Celsius, water is over here and propanone's over here. So we can see that propanone has higher vapor pressure. We're going to cross off choice 3 and 4. Now, intermolecular forces is tied in with boiling point, and where these curves cross, this dashed line indicates the presence of the boiling point. So this right here is 50 degrees is approximately its boiling point, and for water, trace it all the way over here. So we could see that water has the higher boiling point, and if you have higher boiling point, you have stronger forces. So high boiling point leads to stronger forces, and typically lower vapor pressure as a result, because it takes a longer time to get it going. Okay, number 15. A real gas behaves least like an ideal gas. So previously we saw that ideal gases need high temperature, low pressure. Now we're looking for the opposite, low temperature and high pressure. And that's choice 2. I told you we were going to have a least question. Alright, number 16. When a sample of CO2 solid becomes CO2 gas, there is a change in blah 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 blah. Okay. So it's the same substance. We could cross off choice 2. Molecular polarity, still the same substance. Particle arrangement, is that what it says down there? Because it's covered by something. Okay. So yes, actually, it's the change in particle arrangement. Why? Because solids are condensed. So solids are stuck together like this. Particles and particles and particles mushed together. Whereas gases are just free to bounce around everywhere. They're random here, there, everywhere. Particle arrangement, they're arranged differently. Okay, so number 17, I already pulled out table H because it's talking about table H. So we're looking for the substance that has the weakest intermolecular force. So weak, we have to think boiling point, which has the lowest boiling point. So each of these 4 intersect the dashed line, and that's their boiling point. That'll give us propanone as our answer because it's the one all the way to the left. Okay, propanone, choice 3. Yay. Alright, number 18. What total mass is necessary to produce 1 mole of copper? Let me just get rid of table H right now. Ha, disappeared. Okay. 1 mole of copper. So basically we're looking for its molar mass, or its atomic mass, honestly. So you gotta look up the periodic table, so I'm gonna pull that up in a bit. And right here, ooh, appeared right before your eyes. Fancy. Copper is Cu, not Co, that's cobalt. So copper over here. We're looking at its atomic mass. Let's zoom in a bit. And right here it's about 63.5. Let's shrink this back to size and get rid of it. So 63.5 grams is 1 mole of copper, the same as its atomic mass. Number 19. Which gas sample at STP has the same total number of molecules as 2 liters of CO2 at STP? So same number of molecules, again, has to be the same conditions from head to toe. Volume, temperature, and pressure. Okay, so volume is already 2 liters. We just find 2 liters. That's very straightforward. Number 20. Ooh, calculation question. That means we need our calculators, guys. All right. 220 milliliter sample of helium gas, blah, 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 kPa and Kelvin. Whoa. We have a combined gas law because everything's changing. So number 20. What a doozy whopper. Okay. So our initial pressure is 105 kPa times our initial volume of 220 ml over our initial temperature of 275 K equals, on the other side, we're looking for our new pressure, so that's still there, P2. V2 is our new volume of 95 ml. And our temperature is going up as well, so that's 310 Kelvin. If volume goes down and temperature goes up, ooh, pressure is going to increase exponentially. Okay. Plug and chug into your calculator, guys. So I'm going to do this math with you. So first, let's focus on the left side. 105 times 220 divided by 275. Right now, you should have the number 84 thus far. That's my pen rolling. So we should have, as an intermediate step, 84 equals 95 P2 over 310. Cross multiply the 310 to the other side and divide by 95. And P2 equals 274 kPa. So that is choice 4. Woohoo! Alright, number 21. Ooh, yikes. We're talking about mole ratios? Okay, guys, this is an empirical formula type question, which you won't see on your IA, but I guess this was on last year's IA. Anyway, number 21. You're going to solve this empirical formula style. But hey, the numbers are very straightforward and simple. So let me pull out the periodic table for a bit. Okay, let's give me a few seconds. Tapping some buttons here, and open, and done. Oh, don't lag on me. Oh no. Oh, okay. Alright, sorry, I thought this program was lagging and about to shut down on me. Okay, so let's bring this over to a suitable location so we could see. Alright, beautiful. Now we're talking about zinc, carbon, and oxygen. So this is my formatting way of solving empirical formula type questions. So I like to start by writing out the elements that are present. For those of you curious enough to want to learn how to do this question, please follow along. Otherwise, you can just already skip ahead to 22. Alright, zinc, carbon, and oxygen each have those masses. So 65.4 grams of zinc, 12 grams of carbon, 48 grams of oxygen. Okay, now look at their atomic masses here. Zinc happens to be 65.4, carbon is 12, so those so far match. Oxygen's 16, so it doesn't match. So what we're going to do, we're going to convert these to moles. They give us the masses, we're going to divide them by their atomic mass to find the moles. Feel me now? Okay, alright, let's go. So we're gonna get 1 mole over here because this matches its atomic mass, another 1 mole here, and voila, actually 48 divided by 16 will give us 3 moles of oxygen actually. So these are the mole ratios actually, zinc, carbon, and oxygen. So 1 to 1 to 3, choice 2, voila. Number 22, which substance has the greatest molar mass? So what you have to do is actually calculate for every single one of these compounds. H2O2. Okay, so you're gonna have to calculate for each of them and use the reference table. Let me just tell you right off the bat that it's definitely going to be I2 because that element itself is really huge and overpowers everything else, but let's calculate it for a brief moment. Okay, so I calculated right off the bat for you guys, and if you could see that I2 is indeed the largest of the 4, just because the element itself is so huge. It's over 129 grams for every single iodine atom. But by now, you should at least have that skill of being able to calculate molar mass, so I'm just going to gloss over those and just pop out the numbers for your reference. Okay, so number 23, what is the percent composition by mass of carbon in that given formula of ammonium carbonate? So they already save you the step of calculating for the gram formula mass of 96 grams per mole. So that's our total. So you're going to use the formula from the reference table. Okay. Percent comp equals part over whole times 100%. So the mass of our part, we're talking about carbon, and if you look in the formula, there's only 1 carbon. So 1 carbon is 12 grams. 12 divided by its total of 96 times 100, and you should get about 12.5%, which is choice 1. Okay, number 24. A sample of helium gas is in a sealed rigid container. What occurs as the temperature of the sample is increased? Okay, so as temperature goes up, we're thinking about motion because it's tied into kinetic energy. Temperature is related to kinetic energy, which is related to motion. So as that goes up, so does its motion. Okay, so with more motion, they're more likely to bombard and collide with each other, and really, the rest out of these choices, it has to be choice 4. The frequency of collisions increases. They're just going to keep bumping and colliding with each other more if they move really fast. Number 25. Which setup is correct for calculating the mass of 0.3 moles of calcium hydroxide? Okay, so this number 25 is going to need a formula, so we're going to need number of moles equals mass over gram formula mass. So the gram formula mass we actually have to calculate. So I'm going to do this in a separate section over here. So calcium hydroxide. Pause for a moment. Okay, so you'll get 74 grams per mole, because there's 1 calcium, 2 oxygens, and 2 hydrogens. The number of moles they give us is 0.3. So we're going to do 0.3 equals mass over 74. To get mass, we're going to need to do 0.3 times 74. So it's a cross multiply to get the mass. And that is choice 3. Okay, number 26. What is the approximate percent composition by mass of CaBr2? Okay, formula mass is 200 grams per mole. So they save us that extra step. We need to find that calcium, well, I already know this off the bat, off my head. Calcium is 40 grams and Br is 80 grams. But since we have 2 of them, our total is going to be... Oh, they already give it to us. Bro. Okay, so I'm going to do BR2 is going to be 160. It's easier to pick calcium because there's only 1 of that. So what you're going to do is find calcium's percent composition equals 40 over 200 times 100%. So that's about 1/5 of 200 actually, times 100. That's 20% for calcium. That makes bromine to be 80%. Choice 1. Alright, next question, number 27. It's another, looks like combined Cass laws. Oh geez, this is a heavy calculation. So I'm going to pause and give you the... Alright, so this is what the setup looks like for you guys. And if you do this correctly, you should get 52.5 ml as your answer. Whoa, what the heck was that? Oh boy. My pen's acting up, guys. It's time for a new pen. Choice 2. Alright, final stretch. Last 3 questions. Last one, fast one, guys. Oh, that's such a swimming saying. But anyway, let's start. Number 28. Pressure and temperature. We're looking for the relationship between pressure and temperature. As we increase the temperature, what happens to the pressure? As it becomes hotter, the particles move really, really fast and they start to collide. And as they collide, they're going to exert pressure. So more collisions means more pressure. Oop. I meant to pick choice 1. Okay. Number 29. What is the total number of neon atoms contained in 20.2 grams of neon gas? Okay, so this is kind of hard in a sense, but it's not as bad. So it might seem you need dimensional analysis, but you don't really need to, and I'm just going to show you why. So 20.2 grams of neon gas divided by its atomic mass of also 20.2 grams per mole leads to 1 mole of neon gas. If you have already 1 mole, if you remember Avogadro's number, 1 mole is already 6.02 times 10 to the 23rd. And that's choice 4. Number 30. A real gas behaves most like an ideal, so we're basically thinking ideal, is high temperature, low pressure. Choice 1. And we're done! Alright, that's the end. Hope that was helpful, guys. But anyway, I'd like to also give a special shout out. Please go subscribe to his channel for future chemistry videos. Mr. Coutinho, your boy. But the original, your boy was my boy. Just so you know. Okay. So please make sure you guys study. There's a lot you still need to remember, as well as things you just need to know how to do. So this test is definitely a mix of skills and content. So make sure you do your best to review both. But anyway, best of luck. Rest up this weekend and see ya.